Good morning, everybody. My name is Sebastian Palacio Mejia, and today I'll be giving a presentation on characteristics of carbon nanotubes for my materials science project. To begin with, we will do a brief overview of what carbon nanotubes are and how they were discovered. So what are carbon nanotubes? Carbon nanotubes are a carbon-based nanomaterial that is composed of graphene sheets in a tubular structure. And if you're unfamiliar with what graphene sheets are, they're basically just a layer of carbon atoms arranged in a hexagonal lattice. And a hexagonal lattice is also known as a honeycomb. Two main types of CNTs are single-wall CNTs and multi-wall CNTs. Single-wall CNTs are composed of a singular layer of graphene roll-ups, and multi-wall CNTs are composed of more than two layers of graphene roll-ups, which are bonded together by van der Waals forces. CNTs can range in size as the diameter depends on the chirally, which is also known as the twist of the structure. The discovery of carbon nanotubes is actually a very divisive topic in this field. There's various people that claim to be the ones that discovered carbon nanotubes, but only a few are credited to it. In 1952, Rodishvik and Lukijovic published the image of 50 nanotubes in the Soviet Union for the Journal of Physical Chemistry. However, due to politics, these findings were largely ignored. In the United States, John Abrahamson presented evidence for CNTs at the 14th Carbon Conference at Penn State in 1979, and the discovery of CNTs is ultimately credited to Ijama and Ishihashi in 1991 due to their work in producing single-wall CNTs and spreading awareness of CNTs. In the next few slides, I'll be discussing about the material properties for carbon nanotubes. Starting off with thermal properties, for long multi-wall CNTs, they have the best thermal conductivity. Thermal conductivity usually tends to increase with weight percent of composites. In comparison, like thermal conductivity, long multi-wall CNTs tend to have the best thermal diffusivity compared to short multi-wall CNTs and medium-length multi-wall CNTs. So for mechanical properties, single-wall CNTs are typically stronger than multi-wall CNTs due to the forces that interact between each layer in multi-wall CNTs. This basically just means that in multi-wall CNTs, as I stated earlier, they experience van der Waals forces, which tends to decrease their strength. Both single-wall and multi-wall CNTs are extremely light with a density lower than steel. And for the Young modulus, for single-wall CNTs, it ranges from 2.8 to 3.6 TPa, and for multi-wall CNTs, it could range from 1.7 to 2.4 TPa. Lastly, I will be talking about the electrical properties for CNTs. They could experience both metallic or semiconducting behavior, and this behavior depends on its chirality and diameter. If it's semiconducting light, their band gaps will depend on the diameter. Smaller diameter will lead to a larger band gap. High electrical conductivity. For electrical conductivity to increase, it depends on the length of CNTs as well as its weight percent of composites. Now we'll be discussing characterization methods for CNTs. I do want to add on that there's multiple ways that you could characterize CNTs, but I decided to use the two methods that mostly stuck out for me. When it comes to characterization methods, I decided to talk about Raman spectroscopy and X-ray diffraction. Both of these methods are the ones that caught my attention the most. When it comes to X-ray diffraction, it's very similar to diffraction patterns to those of graphite, thus this is not really useful. And I wanted to present this figure 4 just for you to see that both graphite and carbon nanotubes, if pure, they're mostly made out of carbon, so that's why they could be difficult to distinguish between both. And when it comes to Raman spectroscopy, it's one of the most famously and commonly used characterization methods for CNTs, and some of the properties that it could experience is RBMs, which is a low frequency peak, which is less than 200 centimeters. It has large structures like around 1340 centimeters. This is a residual ill-organized graphite, and it's a highly frequency bunch of about 1500 to 1600 centimeters, which are the G bands, which are superimposed and correspond to stretching mode. Now I will be demonstrating my 3D model for carbon nanotubes. I solely did this presentation, or at least the model, on multi-wall CNTs, as I thought single-wall CNTs were not as interesting, as they're only one rolled up sheet of graphene compared to multi-wall CNTs having various amounts of graphene sheets rolled up. So this is my 3D model of carbon nanotubes, specifically a multi-wall carbon nanotube. As you can see, it has 3 layers, and you can see as I zoom in closer that it is made out of those hexagonal lattices, which are also known as honeycombs. As you see, these aren't necessarily attached to one another, but they do have van der Waals forces that make them stay together. This one specifically is about 10 nanometers long. Now I'll be discussing about carbon nanotubes application in pharmaceuticals. I specifically chose pharmaceuticals as this is the field that's most interesting for me. So when it comes to pharmaceutical applications, there's different ways that carbon nanotubes could be used, but I want to focus on these two. There's photothermal therapy of cancer using CNTs. CNT's ability to absorb light in the near infrared region results in heating of the CNTs, and this property of CNTs allows it to be exploited as a method to kill cancer cells through thermal effects. Similarly, carbon nanotubes could be used as carriers for drugs, genes, and proteins. Non-spherical nanocarriers have been reported to retain in lymph nodes for longer periods compared to spherical nanocarriers. So single-wall CNTs have been designed as carriers as a form of treatment for chronic myelogenous leukemia. So now I wanted to wrap up this presentation and share my final thoughts. So in conclusion, we learned about the main types of CNTs and how the discovery is still highly disputed. We learned about carbon nanotubes and how they have great material properties that make them unique as a nanomaterial. We learned about characterization methods such as X-ray diffraction and Raman spectroscopy that helps differentiate properties for CNTs, and how CNTs have several applications other than pharmaceuticals that could help advance many fields. These are the references I used for this presentation, and thank you for your attention.